Good morning and welcome to this next lecture on vibrations of plates and shells. Right at the outset I want to make a statement. When we have circular geometries that are closed, okay, closed in the circumferential directions. For example, we have either a ring or let us say a cylindrical shell that is closed like this. I did make a point last time that there will be modes of the form cos n theta and there will also be modes of the form sin n theta, because any one of these will not capture the entire displacement. So we did have let us say for the ring, okay, for the ring let us say we have u3n given by a n cos n theta and u theta n given by b n sin n theta, okay, that this will be cos n theta and this will be sin n theta. That is decided by the PDE, that is decided by the PDE, okay. For example, if I just take the first equation, we have d by a fourth d2 d theta square u theta n minus d3 u3n by d theta cube plus k over a square d2 u theta n by d theta square plus d u3n by d theta plus rho h omega n square u theta n equal to 0. It is one of the equations, okay. So if u theta n has sin n theta and u3n has cos n theta, then you get two derivatives back to sin n theta, three derivatives of u3, two derivatives bring it back to cos, three derivatives bring it to sin. Similarly, two derivatives will bring it to sin and one derivative of this brings it to sin. You see the theta form and the u3n form have to be related in this manner so that this displacement falls out of all the derivatives, okay, so that I get an algebraic term multiplied by sin n theta outside, okay. If these two are not related in that fashion, if this is not cosine n theta and correspondingly this is not sin n theta, you may have this left with sin n theta and this left with cos n theta, and you will not have an algebraic expression with a steady sign term, okay. So this relationship is decided by the PDE. However, because of completeness, in order to represent displacement in the circumferential direction, if there is a cosine n theta u theta n sin n theta, then there has to be a parallel a n star sine n theta here also, and in parallel some b n star cos n theta also. Okay. So this and this form one part of the mode, and this part form the other part of the mode. So they must be considered. Okay. Otherwise you will not be able to represent the full displacement in the theta direction. I showed this last time. Okay. So when you do this shifting, what will it do to the matrix? Okay. If we have, let us say, this form, then if the operator is used on these equations, what we get is rho h omega n square minus n4d by a fourth minus k by a square, and then minus n cube d by a fourth minus n k by a square. Here we get minus n cube d by a fourth minus n k by a square, and here rho h omega n square minus n square d by a fourth minus n square k by a square into a n and b n. Okay. So by the proper use of these modes, we have made it into an algebraic matrix and the coefficients. The spatial dependent expressions are gone, okay, got removed. So you get, from here you get this, and from here you will get it slightly different. Okay. So let me do it here. So this becomes a plus, this will become a plus, this will become a plus, this will become a plus if you use the blue, this one. Okay. You use this one. So you can see that earlier this was a minus, this was a minus, this was a minus, this was a minus, which gave you certain determinant, let us say determinant 1. But now that again these are pluses and these are pluses, you will find that the determinant is same, and therefore natural frequencies remain the same. So natural frequencies for these set of modes and for these set of modes remain the same, they are the same. Okay. After all, this is just a rotated version of this, okay, and therefore natural frequencies are same. Okay. Now, so what is the difference? What is the difference? So what we will do is we will take n equal to 1 as we did before. Okay. So this becomes d by a4, k by a square, d by a4, etc., and I will drop the d again, n square d by a square in comparison to k square as we did before. Okay. So if we do that, what we get for n equal to 1 is we will get rho h omega n square minus k by a square minus k by a square minus k by a square rho h omega n square minus k by a square for first case a n and b n, and for the second case we will get the same thing, rho h omega n square minus k by a square plus k by a square plus k by a square and rho h omega n square minus k by a square, a n b n. Okay. You can see that here is where the difference comes in the sign here, and therefore determinant is the same. Okay. Now if I take the determinant, what do I get? I get rho h omega n square minus k by a square whole square minus k by a square whole square equal to 0. Okay. And if I solve this, I get for one case omega n is 0, the other case I get a value rho h omega n square minus 2k by a square is 0, and therefore in one case omega n is 0, in the other case rho h omega n square is equal to 2k by a square, and we can compute this. Okay. Now if I go ahead and relate a n to b n in this case, okay, so I have rho h omega n square minus k by a square into a 1 because n is 1 minus k by a square into b1 is equal to 0, and we are looking at the non-zero value, let us say. So rho h omega n square is 2k by a square, so here I get k by a square, a1 is equal to k by a square b1, which means a1 is equal to b1. Okay. And our expression was what? u31 here was a1 cos theta, and u theta 1 will be, because a1 and b1 were equal, a1 sin theta, n is 1. Okay. Now if I look at how the displacement works out, okay, so at theta equal to 0 my u31 is here, cos theta, cos 0 is 1, sin theta is 0, at theta equal to 90 degrees cos theta is 0 and sin theta is positive, so I get this displacement. Okay. Then at theta equal to 180 degrees cos theta is negative, so I get this way, and here at 270 degrees again cos theta is 0, sin is negative. Okay. Therefore I get this. Okay. So it's this n equal to 1 mode, whereas the ring moves this way, the compression begins to happen over here. We have seen this. Okay. That is for this set of modes, this set of. Okay. Now if we go ahead and take the other one, that is this one, okay, because the sign has changed, what will happen is u31 will be a1 sin theta and u theta 1 will be minus a1 cos theta. Okay. So if we try to look at the displacement here, okay, so you see the change here, this was cos theta, this is sin theta, this is sin theta, this is cos theta, but the relationship is different now, although the natural frequency was same. Okay. So now if we try to look at this displacement, at theta equal to 0, I get 0 and I get theta 1 is negative, so I get this displacement. At theta pi by 2, u3 is positive, so I get this, and u theta is 0. At theta equal to pi, sine is 0, okay, whereas cos pi is negative, okay, and I have a negative, so it is positive, so I get a positive u theta. And then finally at 3 pi by 2, sine is negative and cos is 0, so I get this. So you see it is the same displacement. The same displacement is just rotated 9 by 90 degrees. Okay. So nothing radically happened between this choice and that choice. Okay. But what it is telling us is that indeed you need both cos theta and sin theta to fully represent. For example, this behavior could be oriented in some fashion. Okay, this behavior could be oriented in some fashion. That cannot be oriented if you do not account for both cos and sin. Okay, if you account for cos, you are getting one way, you are using sin, you are getting the other way, but the actual situation could be in some other direction. And therefore what this situation is saying is that A1 star sin is needed and let us say B1 star cos is needed, both are needed. Okay. So this way both are needed to represent the full displacement, and this way the relationship is dependent on the PD, okay, the type of derivatives you have. Okay. Finally though, which way will this be oriented? Which way will the displacement be oriented, whether this way or this way or this way, that is completely determined by the exterior force. Exterior force. Okay. What fraction of cos theta will be taken, what fraction of sin theta will be taken in u3, and then how it will be oriented, whether n3 for example will orient like this or it will orient like this, that is completely decided by the exterior force. So I want to mention this right in the beginning. Okay. We will see this when we come to forced response. It is a little bit away, but we have a few topics to cover. Anyway, our final objective is this, to compute the forced response. So we will come to it in after some lectures. Okay, but please note this, that for any one type of displacement you need both to capture the entire displacement. But this relationship between u3 and u theta is decided by the PD. And finally, what fraction of sin theta will combine with what fraction of cos theta is decided by exterior force. Okay. So now let us look at the next system. Okay. So next system is a cylindrical shell. Cylindrical shell. Okay, so we have a cylindrical shell. and it is simply supported on both ends. So, I will discuss what this simple support is for the cylindrical shell. But before that, so let us say there is a differential element cut out from the shell. Okay. So, how does it look like? It looks like this. This length is dx. Let us say this angle is d theta. So, this is d theta by 2 and this is up till the mean, it is a. Okay. And these are the other surfaces behind. Okay. And let us derive. So, what is the objective here? Let us derive the 3 equations of motion in terms of the resultants. Okay. So, we have done all of this in an automated fashion using the Hamilton's law, but here I am going to just show you resultants and the force balance. Okay. So, let us do the x equation first, x equation. So, we have nxx, then we have nxx plus del nxx by del x dx. Okay. Then this shear resultant will contribute, okay, n theta x, this is n theta x and this is n theta x plus del n theta x by del theta d theta. Okay, there will be no other component contributing to the x direction, that is the x direction. Okay. So, if we do a force balance in the x direction, I have nxx plus del x nxx dx. You make it a full force because it is resultant. So, multiply by a d theta. Then the force on the negative side, which is minus nxx into a d theta. Then the shear force resultant plus n theta x plus del n theta x del theta d theta into dx, okay, to make it a full force dimension. Then minus n theta x into dx, that is equal to density into a d theta into dx, that is area, into thickness shell, so this is volume, then ux double dot. Okay. So, now this will cancel, this will cancel and we end up with del x nxx a dx d theta plus del theta n theta x d theta dx is equal to rho a d theta dx h ux double dot. Now if we divide by a dx d theta, we get del nxx by del x plus 1 over a del n theta x by del theta is equal to rho h ux double dot. Okay. So that is the equation of motion in terms of resultants in the x direction. Now what about the theta equation of motion? Okay. For theta equation of motion, that's my element. So this again is the angle d theta. Okay, I'll force it here, d theta. This length is dx. Okay. Then for the theta direction, I have n theta theta. On the negative side, I have n theta theta plus del theta n theta theta d theta. Then what else contributes? Okay. So for this I have taken this as the theta positive direction, okay, and this as the x positive direction. So what else contributes to, so I get a on the x face the theta direction, a negative force nx theta, and this is the incremented nx theta plus del x nx theta dx. Okay. What else? We have the q theta 3, okay, q theta 3, and the incremented q theta 3 plus del theta q theta 3 d theta. Okay. Then that's about it. Okay. The way I would still like to stick with a right-handed coordinate system. Okay. So let's, for this case, take theta to be alpha 1, x to be alpha 2. Then we don't have a problem. We'll stick with the right-handed coordinate system. Okay. I was a bit worried about that because I started off earlier and my x was alpha 1 and theta was alpha 2, and so my theta was, x was this way and theta was this way. Okay. But here for this force balance, somehow I started deriving by taking theta positive this way. Okay. So if we still want a right-handed coordinate system, theta is this way x is that phase, this is alpha 1, this is alpha 2, and we have alpha 3. Okay, so not a problem. So now if we have to do a force balance, okay, if you have to do a force balance in the theta direction, you will have the shear force resultants, the normal resultants, and components of the vertical shear. Okay, so how will it work out? We will have n minus n theta theta into dx, which is a full force now, plus n theta theta plus del del theta n theta theta d theta into dx, that is now a full force, then minus nx theta into a d theta, which is a full force, plus nx theta plus del nx theta by del x dx into a d theta. And lastly, there will be a contribution from the vertical shear, because we have, if you look at the profile, it looks like this. So now we have q theta 3 and q theta 3 here incremented, plus del q theta 3 del theta d theta. Okay. So now this will have a component in the theta direction, this will have a component in the theta direction. Okay. So if this angle is d theta by 2 and this is d theta by 2, we want the sine component. So sine component is multiplication by d theta by 2, and this is a smaller increment, it will get neglected. So we get q theta 3 into dx made into a force into d theta by 2 for this force. Similarly, plus q theta 3, okay, made into a force with dx into d theta by 2. So this will get added. So we get plus q theta 3 into dx d theta. Okay. So that is equal to density A dx d theta into h into del 2 u theta del t square. Okay. So now this cancels with that, this cancels with this, and if we divide by a dx d theta, I get 1 over a del del theta n theta theta plus del n x theta by del x plus q theta 3 by a is equal to rho h u theta double dot. Okay, so that's the equation of motion. Okay, so I'll close the lecture here. We are running out of time. I'll continue from here in the next class. Thank you.